We will now go through the model options under Building Analysis dialog. Click Material and section Effective Stiffness Factors. Here, you can review and change the stiffness factors for all elements type. The stiffnesses table will only be applied for load cases, with Use Crack sections checked in the respective load case editor, except for seismic load cases, where crack sections are always assumed. Building analysis must be repeated each time the effective stiffness factors are changed. To prevent large torsional forces in primary beams due to secondary beams, the global torsional stiffness factor is by default set to 0.1 or 1%. It is the user's responsibility to input all the factors that may be required by the code or according to his preference. Click Cancel to exit without any changes. Storey's degree of freedom. Click on the drop-down menu to expose options. X/Y and torsion permitted means translations in X and Y directions, and floor torsion about Z-axis are permitted. This option should always be chosen for regular, freestanding structure. As we go down the options, we are restricting more degrees of freedom. For example, the last 2 degrees of freedom options are useful for the analysis of a 2D frame system defined along the unrestrained direction.
Rigid zones options affects the analysis assumption at the beam and column joints, beam-to-beam joints. There are 3 options. Maximum, reduced by 25%, 50%, and none. There is an option to specifically disregard and ignore rigid zones in beam-to-beam joints.
The diagram here illustrates the rigid zone and the options. During the analysis, the analytical wireframe of the column is assumed to be at the center line of the column. The analytical wireframe of the beam is at the top of the beam. For rigid zone equals none, analysis calculates and returns the results right at the analytical wireframe nodes of member ends. Generally, this will result is the highest forces amongst the 3 options. The effective length of the member is considered equal to the full length. Rigid zone equals maximum. When full rigid zones option is requested, the analysis program still calculate the results at nodes of member ends, but returned forces or moments are those transformed to the rigid zone ends, which is at the member faces. Rigid zone equals reduced by 25%. This is equivalent to 75% rigid zone. The analysis still calculate the results at nodes of member ends, but returned forces or moments are those transformed to the 75% rigid zone ends, which is equivalent to 25% from the member perimeter section. We highly recommend you use rigid zone equals none as the first choice. Consider the other options if more economy is preferable later. Beam section in analysis model. Default rectangular. There is an option to consider the flange defect due to slab, which will generally reduce the lateral deflection of the model. Soil structure interaction. Default is user-defined support. This means the supports are automatically created at bottom of vertical elements in Storey 1, as defined in the column parameters. Merged foundation model. This feature enables foundations to be integrated into building analysis model. For example, effects of how the settlement of foundation will influence the forces in the superstructure members can be investigated. Obviously, if this option is chosen, foundation elements, such as foot or raft foundation, must also be modeled. Go to Shearwall Model tab. The Shearwall model options are Mid-Pier Model or Finite Element Shell Model. This is a global setting, which will be used if in the individual shear wall properties, the wall model is set to default. However, if in the individual wall properties, the wall model option has been changed to either mid-pier or finite element, then the local individual wall model selection will overwritten by this global setting. Our recommendation is to specifically specify finite element shells model only for walls that requires it in the individual wall properties. Then leave this global setting as mid-pier. This is more efficient than forcing all walls to use finite element in this global setting. Go to Slab Model tab. Storey Diaphragm Model. There are 3 options. Default is slabs to define rigid diaphragms. The analysis will find any discrete areas of interconnecting slabs and set up discrete diaphragms as appropriate. For example, if the floor has two discrete towers, two separate diaphragms, and separate notional loads are calculated and applied to each center of diaphragm, nodes that are constrained by diaphragm will move and deflect as a single entity. Single rigid diaphragm per floor level. The analysis will apply a single diaphragm constraint to every node at any given level. The existence of slabs is completely ignored or irrelevant. A single diaphragm will be formed, even if there are two separate towers modeled. A single notional load is calculated and applied at the overall center of mass. Hence, the entire floor nodes will deflect and rotate as a single entity. No rigid diaphragm floor levels. If you have defined slabs, but for some reason you do not wish a diaphragm effect to be considered, you can completely eliminate diaphragm constraints using this option. In this case, notional loads are applied separately at every node in the floor level. Hence, all nodes are free to mode and deflect separately. If you pick either of the first two options, you can further define which floor to consider diaphragm. The floor that is unticked will assume the third option, no rigid diaphragm. Ensure all stories is selected. Finite elements mesh includes slabs in building analysis. By default, floor slabs are not meshed. That means the physical slab itself and its stiffness is completely ignored in the analysis. The loadings of the slab are calculated and applied onto the beams as external loads. Checking include slabs in building model enables meshed slabs to be considered together with the building analysis. This means the stiffness of the slab can be considered acting together with the frame elements. This is a useful feature if you are modeling flat slabs or transfer plates where walls and columns may sit directly on a slab. It's also useful if you wish to look more closely at the interaction of the slab together with the frame, especially for irregular layout and configuration. If you pick to include slabs in the building model, there is additional option to choose which floor slab to mesh. Check the floors you wish to mesh the slabs. In this training model, we will not include slabs, since all slabs are properly supported by beams. Hence, uncheck this option. Go to the Settings tab. Issue warnings for cantilever beams not marked. If free end of the beams are not specified in the model, then program will display a warning to mark this free ends. If this option is unchecked, no warning will be displayed. If individual cantilever beams marking have been manually done, via mark free end of cantilever beam. If you are sure the cantilever marks are done properly, you can uncheck this option to suppress this warning. Issue warnings for unsupported columns before analysis. If columns or walls in the system are left unsupported, warning messages will be displayed to alert the user. Column may not be sitting on another member or may not be assigned a support at the lower joint. In case of such a warning, you must go back to modeling views and correct the model. This feature can be disabled by unchecking this option. Print column, wall and beam section properties in post-analysis report. Members section properties can be included in the post-analysis report by checking this option. We recommend to uncheck this option to conserve resources. Create detailed analysis echo file. This file is the solver input file, which contains data such as joint coordinates, etc. We recommend this option is unchecked to conserve resources. Use sparse solver for building analysis. The purpose of the sparse solver is to reduce the time required for analysis. For certain model types, a dramatic reduction in the analysis time can be achieved. Example, models utilizing the finite element shell model for walls or very big models. We recommend you always check this option. However, the sparse solver is more stringent and less forgiving on modeling errors such as unsupported members and instability. If the model does not run to completion, try switching this option off. Total and relative horizontal drift limits. The building horizontal drift check is automatically carried out in the analysis and included in the post-analysis checks report. The limit values for the total horizontal drift and relative horizontal drift values defined here will be used in this report. Total horizontal drift is the ratio of the floor horizontal displacement under consideration to the height of the same floor with reference to the ground level. The relative horizontal drift is the ratio of relative floor horizontal displacement to the height of that particular story. To re-emphasize, this is a ratio input. Example, if the limit is 1 in 1000, enter 0.001. Please note these limits are entirely user decision. The default limits does not follow any code of practice. Hence, please enter your own limits. Axial load comparison tolerance. If the default 5% tolerance is exceeded, then a warning will be shown. This report will be explained in detail later. Storey weight and center of gravity calculations. After the vertical loads are defined on the system, they are decomposed onto the beams and reaction values are calculated at the nodes. These reactions are also regarded as masses at the joints. If Use Decomposed Loads option is selected, then masses in the joints are used in center of gravity and weight calculations. If there are no beams in the system, like in flat slabs, then Use Undecomposed Loads option should be used. This option can also be used for beam and slab system.